Just a little refresher on what NIRCam is. It's a near-infrared imager that has two wavelength channels. There's a short wavelength channel that goes from 0.6 to 2.3 microns and a long channel that's from 2.4 to 5. And there's a dichroic beam splitter that allows the fields of view of those two channels to overlap on sky. And it's actually two instruments. There's two halves or modules, as we call them, that are identical. And so you get a double field of view, and that's shown at the right. The blue rectangles are the fields of view of the 4 shortwave detectors in each module, and the red rectangles are the fields of view of the single long wave detector in each module. So there's 10 2048 square detectors in NIRCam. We have 13 short wavelength filters, plus a lot of other elements that I'll get into a bit later, and 16 long wavelength filters. So the total field of view is about 2.2 by 4.4 arc minutes. It's not completely filled. As you can see from the picture on the right, there's some gaps in the short wave, and there's a larger gap between the two modules. The PSF is Nyquist sampled at 2 and 4 microns, and the pixel scales are 31 and 63 milliarcseconds. There are coronagraphs for both the short and the long wavelengths, and there are grisms in the long wave channel that are useful for exoplanet time series in particular, and also for wide field slitless spectroscopic surveys that are interesting for cosmology. NIRCam was the primary wavefront sensor that was used for aligning and phasing the telescope during commissioning of JWST, and mostly using the shortwave channel, but at times the long wave channel was helpful as well. And because it was going to be the primary means to align and phase the telescope, that drove the need to have 2 redundant modules. This is a summary of NIRCam's usage during commissioning. So in late January, we powered on the instrument and then did an initial functional check and first photons. We did a bunch of monitoring early on to see whether there was any ice accumulating on any of the optics in the telescope or in the instrument. And then after a few early activities, there were a lot of what's called OTE, that's the optical telescope element of the telescope. So OTE commissioning then occupied a lot of time out until about 120 days after launch. There were a total of 580 NIRCam owned observations. We submitted almost 190 observation scheduling requests. Each observation or group was scheduled independently during commissioning, not like they're doing now. And we had over 120 real-time commanding activities as well. We had no significant instrument anomalies. 1,200 of 2,500 total visits during commissioning used NIRCam. And we were used on 135 out of 155 days after the initial deployments of the observatory. We generated about 40 terabytes of raw data, and the instrument team supported over 500 console shifts. That was 24/7 over about 155 days. So this is the team. That's 36 people, 33, sorry. And Marcia Ricci, of course, is the principal investigator for NIRCam. Martha Boyer was the deputy commissioning lead, who did an awful lot of work to support the overall effort, and then quite a number of people that made really significant efforts to make commissioning happen. Okay, so I kind of made a choice to focus a little bit more on how NIRCam was used in early commissioning, and specifically during commissioning of the telescope. I won't get into the details of how the data were analyzed to support telescope commissioning, but I thought it might be interesting for people to see some of the unique types of data that we collected using dedicated optical elements in the NIRCam instrument. And so I'll go through that, and then with whatever time is remaining, I'll talk a little bit more about commissioning of NIRCam and the fairly small number of issues that we discovered while we were doing that. And then if I have more time, I'll get a little bit into more detail about the actual performance of NIRCam as characterized during commissioning. So a few days after we powered up the instrument, we were at very elevated temperatures. The long-wave detectors actually weren't even working yet. They were so warm. But the short-wave detectors were all working. And so we got these early images. You can see that there are 8 detectors there, and they're all taking images of stuff in the sky. And so that was laid to rest a big worry that we had, which was that we might have a detector that was dead, or one of the readouts from one of the detectors might be dead. And we were able to verify that the long-wave detectors were alive as well and fully functional. They just weren't generating photocurrent at the elevated temperatures at this time. So this looks pretty good. It's confusing. This is, the telescope is still just in the deployment state. So every source in the sky generates 18 images from each of the 18 mirror segments. And each of the 18 mirror segments has different aberrations, different defocus, etc. And so it's cluttered. This was pointed towards the LMC, and so there were a lot of sources and a lot of different PSFs and 18 PSFs for every source. So pretty crowded. This image was actually produced after several days of effort, and it looks pretty sharp. But the first image that we got did not look like that. So this is actually what we saw on that day when we got our first photons images. And you can see that it looks very blurry. So the difference is this had been heavily processed, where people went through and actually differenced the groups in each integration ramp, produced a very short 10-second effective exposure time image, and did that for every group in 4 integrations, and then shifted and co-added those in order to produce this sharp image. If you don't do that, if you just take the 4 integration ramps, compute a slope from each, and then average those slope images, this is what you get. And we had to scratch our heads for a little while as to why it was so blurry. It was a little distressing at the time. We thought, well, maybe things are really out of focus, or we weren't quite sure what. But after a little bit more investigation, what we found was that the pointing for the telescope was actually not stable after you did a slew. And so I attempted to illustrate that here. So on the left, it's an RGB overlay, and the data this is in FO7OW filter. There were 4 100-second integrations, and the red channel shows the first of those, the count rate image from the first of those integrations. Blue is the second of those integrations, and green is the 4th of those integrations. And so what you can see is, as we were taking those 100-second integrations, sources were moving around on the detectors quite a lot. And so if you then projected those all in grayscale, you would just basically see a big blurry image. So after we took the FO7OW data, we took F150W data. That took us about 15 minutes after the end of the FO7O data collection. And then collected F200W data. It's a F2000W. That's not right. It's F200W. With exactly the same exposure parameters. And again, on the right, this is an RGB overlay, but you can see it's much closer to a grayscale because the pointing had settled down quite a lot by that point. Also evident is the slow drift in pointing that occurred between the first filter and the 200W filter exposures. So this actually required quite a significant replan of commissioning, and it added a lot of time because we had to wait about 15 minutes or so for pointing to settle down. And the spacecraft team spent a lot of time trying to tune up their pointing model parameters to get these pointing transients to damp out. But it took a long time. And so for the first couple of months of commissioning, we were dealing with this. And every time you slewed to a new target, or even did a fairly small slew, even slewing from one NIRCam module to the other module, you had to put in a settling observation. And so those were not planned for. And they took up a lot of time and required all the APT programs to be updated to add those exposures in. Okay, so after we got our initial functional check data, which was what I was just showing you, we decided it was okay to go ahead and take what was called the initial image mosaic. And so this was a big mosaic on the sky where we pointed towards a very bright star, but we didn't really know where the bore site of the telescope was yet. We didn't know the alignment between that and the star trackers. And so we pointed towards a very bright star, and we started mosaicing around. And eventually, and actually luckily it was very quickly, we found the 18 segment images from that star, and that's shown on the left. There was a lot more data collected. This is cropped down just to show the actual images from that star. And you can see that the various PSFs have astigmatism and defocus and stuff like that. And then, just out of curiosity, we had some time while the telescope commissioning team was working on those data to take some additional observations with NIRCam. And NIRCam includes a pupil imaging lens in the shortwave channels, which allows us to form an image of the telescope primary on the NIRCam detectors. And we weren't quite sure what we were going to see in this. We attempted to point to the segment that is highlighted in the red circle on the left. And as it turned out, we did pretty well. And we ended up with a very bright segment image from that particular primary mirror segment. And the illumination on the other 18 segments is a little bit mysterious, but it's probably due to just diffuse scattering of light off of those other 18 segments. And you can see in these images, the secondary mirror support structure, there's one vertical one, and these two down here that are slanted at 60 degrees. At any rate, there was another press release image that was kind of a surprise. We didn't really anticipate doing that before we started commissioning. Okay, so then the process was to take those scattered about images. They needed to be associated with the mirror segments. And so what the team did was they tipped each of the 18 mirror segments and watched how these 18 images on the left moved. And they were able to associate each image with a specific image in the primary. And then they steered the mirrors in order to form what's called the image array, which is shown on the right. So this is after, with no corrections to any of the segments other than to just collect up all their images onto a single NIRCam detector. And then there were sort of coarse adjustments to the individual segments. When that was done, we ended up with an image that looked like the one I'm highlighting here. And then after this segment array image array was formed, then there was a fairly complicated set of steps to slowly compress this segment array into what's called a stack. So all 18 images of the single mirror segments are then stacked in the center here. So this is essentially roughly 1.8 meter mirror PSFs all stacked on top of each other. It's not anything like the final quality of the PSF that was achieved. During all of this time, one of the concerns was that there could be water ice coming out of the backplane structure, which was a carbon fiber composite, and it could potentially be accumulating on optics, JWST optics. And so NIRCam undertook quite a difficult series of observations using the long-wave prisms that I mentioned earlier. And this is just showing in green, this was the pre-flight estimate of the throughput. It was our filter transmission plus the GRISM response. And then these absorptions are from a required amount, a maximum amount of contamination due to water ice and non-volatile residues. And so we wanted to make sure that we didn't have any more ice than what's shown in the heavy green lines. And this is module A on the left, module B on the right. And the actual measured data is shown in the red and blue lines. And as you can see, there's essentially no contamination. And that continued through the entire OTE commissioning process. And so we got fairly tight upper limits on the level of contamination, but it's essentially equivalent to not having any. So that was good news, and it was a lot of work to get that answer. The next thing we had to do after getting all the images stacked was we needed to check that NIRCam was well aligned to the primary mirror, and so we used the pupil imaging lens. So again, you can see the telescope primary mirror and its 18 segments and support structures. And then the nice thing was that in this picture, I don't know if you can see it on screen, but these yellow lines are meant to be slightly outside. You can see maybe that there's an edge here. It's fairly clear down on the lower left. There's an edge there, and an edge there. On those edges that are well outside the primary mirror pupil are the internal NIRCam pupil. And the good news was that even though we can't really see our internal pupil around the right hand and upper right hand edge here, by being able to see these edges on the left and lower left, we knew that we were well aligned. And so that was put our minds to rest about that. And then we also have to make sure that one of the wavefront sensing elements, these are called dispersed Hartmann sensors, were well aligned to the telescope as well. And so on the right, I'm showing another pupil imaging lens image, and in red is an image like the one on the left. It's actually the same as the one on the left. And then in green is what's called the DHS 0, so 0 degree orientation apertures. And so we're looking through an element that's got apertures in a pupil wheel and seeing how those apertures line up against the segments in the telescope primary. And then purple are the, actually it's blue, the blue channel, that looks purple here, are the DHS 60. And so you can see that each of these apertures, the greenish ones or the purplish ones, cover two of the segments of the primary mirror. And they come by pairing up the zeros and the 60s. These two pair up these three elements, these two pair up these three elements, et cetera, et cetera. So you can, what these apertures have in them is a GRISM. And so they generate a spectrum, and you can use that spectrum to determine the piston offset between the mirror segments. And so we took these pupil imaging lens images of the DHS elements in both modules, and these are more finicky in terms of their alignment. On the left, it's like, okay, we're in the imaging pupil pretty well. We would probably be perfectly happy with that for the rest of the mission. The ones on the right, we wanted to tweak a little bit to get the alignments a little bit better. We're kind of crowding some corners here, and things like that. And so we actually did adjust our pickoff mirror on one module in order to improve the alignment of the DHS elements. And so that was a requirement to enter what's called coarse phasing for the telescope, which uses those DHS elements. As I mentioned, they have grisms in them, and so these are just example spectra from those grisms for the 0 degree and the 60 degree elements on the left and right. And if you look on the, especially in the left-hand image, you can see that there are sort of barber pole stripes across these spectral streaks. And the frequency, the tilt of those barber pole stripes is indicative of the piston offset between the primary mirror segments that are included in each of the 10 DHS apertures. And so you can see this one is kind of a medium frequency. This one is a very high frequency. The second from the top is basically two parallel spectra, so those two are way out of phase. At any rate, that's just to demonstrate kind of how those elements work. Okay, to continue with some other elements that were used for wavefront sensing, we have weak lenses, and these are used to mostly for later parts of telescope commissioning when things are almost in alignment in order to really get the fine-tune the phasing of the entire telescope. And these images were actually taken just after the first image stacking step. So in this picture at lower right, it looks like everything is stacked perfectly. But when you put in a weak lens and take a picture of that stack, you can see that the 18 individual PSFs actually aren't perfectly stacked. So this helps diagnose the stacking process. The defocus is characterized in number of waves at 2.1 microns. So that's what this plus or minus 4.8 waves stuff is. So this is just an example of the kind of data we got, very early in commissioning after we did the first stack. This is what those images look like after we had completed phasing against the NIRCam instrument. So up until about L plus 75 days, we were only looking at how the telescope was aligned relative to NIRCam. So these were the final images of the stacked and phased PSF after that alignment to NIRCam had been completed at launch plus 76. Final alignment was completed at launch plus 120, which accidentally was within hours of the estimate in the pre-launch commissioning timeline, in spite of all the problems that we had with the pointing instabilities and things like that. And that was because we were able to cut out fairly significant parts of the telescope commissioning. Okay, so this was the press release image from when we had finally finished up all of the telescope alignments and phasing, et cetera, et cetera, et cetera. A beautiful image. And just for comparison, at the same scale on the left is the Spitzer at the same wavelength. Not surprisingly, the 85 centimeter telescope doesn't have quite the PSF of a 6.5 meter telescope. But, nice to see that we're getting really, really beautiful images out of NIRCam and JWST at this point. In this data set, went through and pulled out all of these background galaxies. Field was not chosen for background galaxies. It was chosen to image the star that was in the previous picture. But at any rate, it gives you an idea of how rich these data are, especially in the long wave channel for imaging distant galaxies. And it's just really phenomenal how much stuff is out there in kind of any typical NIRCam image that you look at. Okay, so that's sort of the end of telescope commissioning. NIRCam has 5 science modes. and those have corresponding templates in APT. There's imaging with 29 filters, 13 shortwave and 16 longwave. Band passes range from about 1% to over 100% for a couple of the special use filters. And subarrays support bright source imaging. There's the wide field slitless spectroscopy with the grisms in the longwave channel. There are 2 grisms with orthogonal orientations. There are a time series photometry and a time series spectroscopy template or mode. And target acquisition is available in both of those to get very repeatable target placement. And coronagraphic imaging with 5 occulting masks. And again, target acquisition supports highly accurate and precise target placement so that you can use PSF reference stars and roll subtractions in order to enhance the contrast. And all of these, just to remind people, all modes acquire simultaneous shortwave and longwave data of the same portion of the sky. That was not true of coronagraphy in cycle 1, but that's been updated and we expect it to be available for cycle 2. This is just the NIRCam activity flow. So to the left of this vertical dashed purple line is what I was talking about before, sort of the OTE commissioning or telescope commissioning. And then once that was done, we got into the astrometric measurement was sort of the kickoff of everything for NIRCam, and coronagraphic astrometric measurements as well, although those were much later. So this branch sort of feeds over to enabling the coronography mode. This branch feeds over to enabling imaging. Of course, coronography does allow you to do dithers, so there's some interplay here. But, and then, let's see, then there's a branch for the wide field slitless spectroscopy mode using the long-wave prisms. And then there's a branch that supported the grism and imaging time series modes. So just sort of a flow chart for give you an idea of how many activities were involved in. So I'm going to reveal a few of the unpleasant aspects of what we discovered during commissioning with the instrument. None of these were particularly horrible, but there are a few things that people should be aware of. So probably a lot of people have heard about the meteoroid strikes. We see those in the Pupil images of the telescope primary, and so occasionally you look at a new image and you'll see a new black spot like this one that's highlighted in the blue circle at the lower left. And that's from this point on the primary mirror. This was the biggest strike that we've seen so far. It was much worse than any of the others. This was another strike up here. These ringing artifacts are a part of the Pupil optics and aren't anything to be concerned about. They're always there. It looks like we'll get about 16 of these a year, and they do have an effect on the optical state of the telescope. And so when one of these happens, typically they're able to use the actuators on the mirror segments to actually take out the wavefront error induced by the hit, or at least mitigate it. But that means that the state of the telescope is changing over time. And so we're set up at this point to deliver OPD maps of the primary mirror that are date specific. And so you can use those to generate a PSF model for the date of your science data, and that's available now. And we're going to be implementing a micrometeoroid avoidance zone, and that'll be incorporated into APT, and observers will be encouraged to stay out of the avoidance zone, but it won't be a requirement, is my understanding. You might have to write a short justification. Let's see. So this is some images showing some scattered light artifacts that we discovered during commissioning for NIRCam. So on the four on the left are Module A, the four on the right are Module B. And you can see these sort of extended bright streaks and stuff on a few of the detectors. And these are two different effects. The one on the left is what we ended up calling claws. They tend to be these very narrow, kind of look like claw marks in terms of signal brightness on the detectors. They move around. They change their structure depending on pointing. And then in yellow are what we call wisps. And the wisps are essentially fixed in detector space, and they're essentially always there, although the level that they're there at varies. And so it's kind of kept us from developing flat fields as quickly as we might have wanted to. We had to figure out ways to get these out of the data in order to produce actual pixel flats for the detectors. But that's well in hand now. This big red spot here is just due to a galaxy that happened to be in the field of view for this one. The observation that's pictured here. These were studied in quite a bit of detail by Goddard Optics. The wisps are formed by light that's way off the bore side of the telescope. It's rays that are coming probably from diffuse light. It just makes it past the tip of the sunshade, strikes the inside of this secondary mirror support structure, which unfortunately had to be coated in mylar. And then that reflects down and enters what's called the aft optics subsystem, which feeds light down to the instruments. And so we get the wisps from that path, and then the claws are a more direct path. It's about 10 degrees off the bore sight. And again, there's a narrow part of the sky that can enter this aft optic system and then scatter off our pickoff mirror and then off the interior of one of our optical mounts and cause the claws. And we actually mapped out the sensitivity zone for where claws are formed. So if you have bright stars that fall in either of these zones, one is for Module A and one is for Module B, you can get claws in your data. So the wisps are faint generally, and they're consistent. They're fixed. They do depend on wavelength. The claws are typically rather brighter than the wisps. They move around. They change character. And they're not horribly bright, but for really deep imaging, they can be pretty annoying. And so I believe there will be, this is an APT visualization capability that'll be available for cycle 2, I'm hoping. If not for the proposal deadline, I think for replanning accepted proposals, it will be available. And so you'll be able to visualize your observations and check for bright stars in the avoidance zone, and then change your roll angle, pick a different date if you need to get away from that. This was an interesting effect that was not a NIRCam effect, but was actually what's called a mirror tilt event. So this is our first attempt to do a long time series observation. It was of a transiting exoplanet, very high gravity exoplanet, so it has a boring spectrum, but it was a good candidate for a commissioning target because there were no science programs that went to look at it. And so this is the time series in the long wave GRISM data where all the wavelengths were summed, and you can see the transit starts, and then boink, all of a sudden at the bottom, there's this distinct offset, and that persists You can see that the baseline after the transit is also significantly higher than the before transit. It was a bit of a puzzle at first. For the long-wave GRISM time series mode, you actually get simultaneous imaging using a weak lens in the shortwave channel. And so the bottom here is showing the shortwave images. And so it's showing one shortwave image, and then it's showing the ratio of the next image to this first image as a time series as you go across here. So you can see that the weak lens image was very consistent for quite a while. And then all of a sudden you see this little pop, and then it got stronger, and then it stayed the way it was. And you can actually use these weak lens images are exactly what we use to check the wavefront error for the telescope. So if you analyze these images, what you find is that this one segment actually tilted. And this was a known effect that was observed in pre-flight cryogenic testing of the mirror. There's not much you can do about it. You just have to correct it after it happens. And so as it happened in this case, we got it right in the middle of our time series event or observation. And it can basically be taken out by simply shifting the pre and post light curves to overlap. Another issue that was a NIRCam issue was that we found that our this is a drawing actually, but it's basically what you would see if you took a pupil imaging lens image of one of our coronagraphic LEO stops in the long wave channel, and this is for the round masks. So you can see that there are these cutouts that allow light from some of the primary mirror segments to enter the instrument, and so you have to make sure that those are aligned well with those segments. And when we looked at our data from the first long wave coronagraphy, what we found was that the PSF had this extra speckles off to the side, and we made sure that it wasn't due to something that was actually astrophysical. Unfortunately, the long wave channel doesn't have a pupil imaging lens, and so you can't just take a picture like this in order to confirm the alignment or measure the alignment in the long wave channel. So we had to invent a way to do that on the fly, and that involved doing very detailed optical modeling and predictions of the PSFs for having this pattern of openings clocked with respect to the primary mirror pupil. And when we did that, we found that that reproduced the observed pattern of light shown in the upper left for a particular percent of pupil offset. And then that required a lot of extra work that we weren't expecting, and was why we ended up commissioning the coronography about 2 weeks after the end of nominal commissioning. Let's see, the rest is good news. There's a few more slides here. The bottom line is that we exceed all performance requirements for all science modes. And so there's not a lot more to say about that. This is our encircled energy requirements. It's required to be greater than 70%. I think, yeah, this is reference to the pre-flight exposure time calculators. So we get values that are around 1 and then increasing. And we were required to be greater than 70% of the pre-flight. Predicted versus observed encircled energy are excellent. Distortion calibration is excellent in the handful of milliarc seconds range per point, and if you bend those, it gets down to a single milliarc second. The wide field slitless GRISM sensitivity is excellent. So the solid red lines are the pre-flight prediction, and then the blue and green lines are the as measured sensitivities. So well exceeding what we were required to do. This was kind of a fun thing. I think this was in the GRISM calibration data that we took during commissioning. One of the guys noticed these little emission lines and was able to identify that it was a line emitting galaxy at a Z of over 4 in a few 100-second explosion. This is that same GRISM transit data, but with the corrected for the mirror tilt event that had occurred down here. And this is showing just the shortwave image in a shortwave subarray, and the long-wave GRISM spectrum also in a subarray on the long-wave detector. This is showing that we're hitting about 100 ppm noise floor on the GRISM time series performance. That's with this sort of the spectral resolution that's shown here. The fact that there are no spectral features in this spectrum is not a surprise. The source was chosen for exactly that reason. And the detector settling times are short. So this bottom plot is showing the time series on the shortwave channel. And you can see that there's a transient at the beginning here with a response increasing for a time, but then at about 2,000 seconds, it's a pretty good linear approximation to the rest of the data. For coronography, contrast performance is excellent. So we had, there were no actually formal requirements for NIRCam coronography. It was sort of a best effort mode. And so we had a commissioning readiness criterion indicated by this red bar here. And we observed HD 114.174b, which is about here on a contrast curve. And this is showing for a bunch of different dithers with the target behind the coronagraphic mask. And then combining those using roll subtraction and reference star subtraction and clip, you can actually push the contrast down by another order of magnitude, roughly from any single, from the worst case of any of those single exposures. So, doing very well there. Okay, so that's all I've got. The bottom line is we are working pretty well.